Unit 2 activity for exponential regression. In this activity, we will work with the datasets that are best modeled with exponential functions. You will use technology to find an exponential equation that best fits the data, which is the exponential regression, and you will compare linear and exponential models and determine which is the better fit. So here are the learning outcomes. You will define variables, interpret the meaning of values, and explain your reasoning in choosing linear or exponential models. You will also choose an appropriate model for each problem, and you will state assumptions being used. You will use technology to find regression models from data, and you will use tables and graphs to estimate values. Also, you will use regression models in various situations involving real data. Okay, let's start with a warm-up. Fill in the missing parts of the table. Given function, the first one, f of x equals 4 times 1.03 to the power of x. The initial value, just to recall, y is equal to a times b to the power of x. A is the initial value. B is either growth or decay, meaning its growth when b is greater than 1, and between 0 and 1, that is decay. So initial value for the first one is 4. Growth or decay, you see 1.03 is greater than 1, so this is growth. Growth or decay factor, which is our b, so 1.03, and growth or decay rate as a percent, that is 0.3%. 3%, sorry. Then the second one, g of t is equal to 10 times 0.98 t. Initial value is 10. Your growth or decay factor, 0.98, your b, 0.98 is less than 1. So this is decay. And that is our decay factor, 0.98. And when we meaning it decrease by the rate 2%, because 1 minus 0.02 is equal to 0.98, so that's why you have 0.98. Okay, next one, initial value is 1000, and you have the growth factor 1.05 is greater than 1, so this is growth. So we can write here, let's see, y equals 1000 times 1.05 raised to x, and rate is, that is 0.05, so that is 5%. Okay, next one, 30 is the initial value. We have 0.96, so that is y equals 30 times 0.96 the power of x, so that is less, 0.96 less than 1, so this is decay. And when we subtract that from 1, that is, yes, 0.04, so that is 4%. So 1 minus 0.04 is 0.96, so that is your decay factor. Then the next one, 50,000 growth, and that is, what is this, 7.5%. So that is 1.075. So your y here is 50,000 times 1.075 to the power of x. And the last one, with a 49% decay, so what's going to be the decay factor? So 1 minus 0.49 is equal to 0.51. So this is 0.51 here. So this is going to be 200 times 0.51 to the power of x. Okay. With the class discussion. Number 1, revenues from the sale of compact computers are shown in the following table. T as the time in years since 1990. We have 0, 2, 4, and 5, and the revenue are in billions of dollars. 3 billion, 12, 50, and 90. And letter A, we're going to find a linear regression model and an exponential regression model for the data. So we're going to use a technology here. Here using Desmos, we are going to enter our data. So hit plus and you'll see table. And now you can enter our values. So from the table, we have 0, 2, 4, and 5. And for our function, 3, 12, 50, and 90. So now we want to see our points. So meaning we can change the settings. So graph settings, click on this and maybe change our y, the range. So let's say up to 100. Okay, so now we can see our points 1, 2, 3, 4, those green. Now we want to find the linear equation and the exponential linear regression model. So remember, I showed this to you before. If you watch a video using Desmos, you start with y1, y sub 1. Instead of equals, we are going to estimate, so we have to use this symbol tilde, and our equation for a line is mx plus b. So just type tilde m x sub 1 plus b. So if you notice, look at our table. On the top, we have x1 and y1. So you have to use that y1 here and x1 for your x and y. And you will see here our values of our slope, 16.7966, and your b is negative 7.44068. Then the next one is our exponential regression model. So let's click another line here, and you know that our exponential equation is a times b to the power of x. So y1 again, since our table is y1, and then tilde a b to the power of x1. So you'll see the values of a and b. And you can see here also our graphs. The black one is the line and the red one is the exponential. From our Desmos, our linear and exponential regression models for the given data, y equals 16.7966x, b is negative 7.44068, and then for our exponential regression model, y is equal to a is 3.86887 times 1.87913 to the power of x. Now next, fill in the table of predicted revenue values using the two regression equations. Still using the time from 0 to 4 and 5. Now let's use Desmos again to find those predicted values. I type the linear equation, which is 16.7966x minus 7.44068, and here's the exponential. All right, we want to get the values as 0, 2, 4, and 5. So we can change this into a table. Let's click this, edit list, and then click on the table. And then you can just type here 0, 2, 4, 5. 0, let's change it to 4 and 5. Same thing here for exponential. So hit edit list, and then click on convert to table. See that, convert to table. And let's use 0, 2, 4, 5. 0, 2, 4, and 5. So these are our values, and we're gonna copy all this into our notes. So here are the values, the revenue predicted by linear regression and the exponential regression. Okay, and letter C, which equations is better model for predicting revenues? What do you think? Yes, it's the exponential. Why? Take a look at these values. $3.87, that's very close to the revenue R of the given. 3.87 is 3, 13.6 is 12, 48.24, 50, 90.65, 90. So that's why the better model for this is the exponential. As you can see here also, this is our given data, the orange dots, and if you use the linear, the points are not pretty close to those points. But if you try our exponential, look at that, they are very, very close. So that fits our data. Problem number 2. Facebook started 2009 with about 150 million active users, and by 2010 we're over 300 million active users. So letter A, find a linear model and an exponential model for this data, and remember to define your variables and also which functions predicts more users over time. Let's use our variables, t for the time, that is in years since 2009, and let's use u as the Facebook users in millions, and let's use a Desmos for this. Here's Desmos, hit plus to add table. So we have the first one at the beginning, 0, it was 150 million users, and then next is 300 million users. Now we don't see the points. We can adjust our settings. So on the top right here, grab settings, so hit that, and let's change our range. So let's say we have here 150 and 300, so let's say about 500, and now you'll see those 2 points. And let's try our linear and exponential regression model. So y1, remember, then tilde mx underscore 1 plus b. See the green. And how about our exponential regression model? So y 1 tilde AB to the power of x 1. So if you notice, this is the linear mx plus b. We have both the 2 points, and if we use our exponential, it's the same thing for both. So both at 0, 150 and 1, 300. So these are our functions. U of t is equal to 150t plus 150, and our exponential 150 times 2 to the power of t. Again, t is the number of years. And the question, which function predicts more users over time? It's going to be exponential. Let's answer letter B. According to Wikipedia, as of 2012, there were 901 million active users, and as of February of 2013, the number rose to 1.06 billion. Which model from Part A makes better predictions for these dates? So to answer that, let's add our data here. So it was 3 and 901 and 4 1.06 to 1060 users. And let's change our range here. So let's say 2000. Alright, I think this is better. Let's see here. Okay, so with our data now, this is linear. All the points are very close to the line. And these are exponential. They are also close to the line, but which one is better? So take note of this also. You will see here r squared for linear 0.9856, r squared for exponential is 0.9441. R squared is greater than for linear, so that's why the best fit is the linear for this data. Okay, as you can see here, if you look at the line, most of the points are very close to the line compared to the exponential graph. So which model from Part A makes better predictions for these dates? We have the linear. Letter C, you now have 4 real data values for this situation. We have all this for. This data is neither linear nor exponential. Use the data to find the linear equation that best approximates the data. Also find the exponential equation that best approximates the data. So that's what we did last time. And I'm going to write those 2 equations here. Right, so these are 2 equations. This is for linear and this is for exponential. Okay, letter D. There were 1.49 billion active users in 2015. Which model predicts closer to this real value? Let's go back to our decimals. Letter D. There were 1.49 billion active users in 2015. Which model predicts closer to this real value? So this is the real value 1.49 billion in 2015. So in 2015, that's going to be the time is after 6 years from 2009. So let's try that. Let's use with linear. So you're like solving u of 6. 242.1 times 6 plus 118.55 is equal to 1571.15. And if we use our exponential, u of 6 is equal to 226.919 times 1.49374 raised to the 6th power, and this is equal to 2520.69635. So which model predicts closer to this real value? 1.49, that is 1490. So this one, linear, 1571 is very close to 1490. Okay, and then now letter E, graph the data including 6 and 1490 for 2015. Describe the shape of the scatter plot. How does this description support your answer to question D? And what would the scatter plot look like if the other model were a better choice? Let's go back to Desmos. So here I'm gonna add 6 and 1490. So here's our linear, and here's our exponential. Which one's the best fit? So yes, it is linear. As you can see here, also r squared, you see here 0.9911, and for exponential 0.9151. Okay, please try this with Desmos. That's the easiest way to graph linear and exponential regression models. And that's it for Unit 2, Activity 4. Let me know if you have any questions. Thank you.